Okay, so this is lecture 3 of this lecture series. It's the one that's about the standard model predictions for the properties of the Higgs boson. So, in principle, this is a very straightforward subject. We've defined the standard model. As I've described to you, we've tested the standard model in various ways. It so far works extremely well. We add to the standard model at the Higgs boson, that is the Higgs scalar doublet. I used to call this the minimal standard model, because in principle you could add to the standard model multiple Higgs doublets or even more complicated sectors, which have the result of breaking SU2 cross U1. But I think now most people refer to the standard model as the minimal version, with exactly one set of Higgs fields. This has interesting implications, which I'll talk about in just a moment. That model is an extremely predictive model. We basically know the parameters of it, and those parameters are even going to improve as we, in the next 10 years, improve our knowledge of alpha S, the B mass, the charm mass, etc. And in that model, all of the parameters are fixed. The last one to be fixed really is the Higgs self-coupling, which is fixed because we know the Higgs mass now to 3 significant figures. So now we can go ahead and predict all the properties of the Higgs boson within this model completely unambiguously. And then there's the question of, is experiment going to agree with those predictions? That's an interesting question. I'll give you a hint. So far the answer is yes. We'll talk a little about that in this lecture. And it would be good to really fix in mind what the predictions are and what is testable here. So let's talk about this. First of all, I'd like to work out the vertices of the Higgs boson that are relevant for the study of Higgs boson production and decay. And this is a very easy thing to do, because we introduce in the standard model one Higgs field, and we can parameterize that as in this way, where V is the Higgs vacuum expectation value, and H, pi 3, and pi plus and minus are fluctuating fields. However, those pi fluctuating fields are Goldstone bosons. They're eaten when the Higgs field gets a vacuum expectation value and when the W and Z bosons get masses. And so we can just gauge them away. And all that's left is H sitting exactly in this place. So what that means is that when we discuss the non-derivative interactions of the Higgs field, and actually in a renormalizable theory, the Higgs has only non-derivative interactions, then we can just compute them by taking V and shifting by H over V. So all I have to do is to take the standard model Lagrangian. Maybe I should accept the term d mu h squared, which, however, is very simple. I should take d by dv of that, and I should multiply by h, and that will give me the vertices of the Higgs boson. And once you've decided that, you can basically just write all these vertices down. So, for example, the Higgs coupling to a fermion is going to have 1 power of h in it. So there'll be a minus I, the mass of the fermion, the 1 over V, because I'm differentiating with respect to V, that's the V that's in here, and that's it. If I have a gauge boson, in this vertex, the V appears squared, so I'll end up with plus 2I mv squared over v. And actually, it also works for the Higgs boson itself. This is 3I m Higgs squared over V. And so, minus. And so there we are. It's extremely simple. There's no freedom here. These are the vertices of the Higgs boson in terms of the already measured masses of standard model particles. At this point, we could just go start computing the properties of the Higgs boson. But I think it's worth saying a few more words about this, because there's an important story here that I'd really like you to drill into your minds, because it will come up whenever you start talking about beyond the standard model physics. The fact that these vertices are unambiguously given, and in fact very simply given, is part of the material that I discussed yesterday, that the standard model is the most general renormalizable theory, which is SU2 cross U1 invariant, and which contains the known particles of elementary particle physics. So you might have reason to doubt that, because maybe there are some other vertices that you can think about writing down that would alter that. So what I'd like to do now is to kind of make a systematic survey of everything you can write down, which is SU2 cross U1 invariant. Renormalizable means operators of dimension up to 4. And let's just write down all of them. Well, the first thing is the gauge kinetic terms. But the structure of those terms is completely fixed by gauge invariance. If I want a renormalizable theory, that's the only thing I can write down. Secondly, the quark kinetic terms. The quark and lepton kinetic terms, I should say. Again, the structure of this term is completely fixed by gauge invariance. It's the only thing I can write down. And actually, at this moment, I've introduced only 3 parameters, namely G sub s, G, and G prime, the coupling constants of the standard model. There's one more set of terms that you can write down, which are the, what is it, 64 pi squared FF dual, the theta terms. So Nathaniel pointed out that these theta terms can actually be relevant to physics. Actually, the only one which is really relevant to physics is the one for the strong interactions, because as Nathaniel told you, it requires a non-perturbative effect to get this to be active. Nathaniel told you how to get rid of this term, so that's all I'm going to say about it. But aside from that, those theta terms, these are the only parameters that enter at this stage. Now we introduce the Higgs kinetic term. Once again, the structure of that term is entirely constrained by gauge invariance and introduces no new parameters. Then there's the Higgs potential. That introduces 2 new parameters, namely lambda and mu squared. But these are completely determined by the Higgs vacuum expectation value and the Higgs mass. Maybe I should say that because we have a 1 Higgs theory, there are only 2 parameters that appear here. Oh, sorry, that should go there. If we had a 2 Higgs theory, there would be, 3 mass terms and 4 coupling constants. I'm not exactly sure, but the number of parameters rapidly proliferates with the number of Higgs fields. But with 1 Higgs field, it's 2 parameters, both of which are readily exchanged for observable quantities that we can see in standard model experiments. And then finally, there's the Higgs coupling to quarks and leptons. And those appear in the following structure. Y, L is a left-handed lepton doublet, L dagger dotted into phi E right minus y d. Q dagger is a left-handed quark doublet dotted into phi d right, and then y u Q dagger a epsilon a b phi dagger b u right plus Hermitian conjugate. Now, at this point, we've actually introduced a very large number of parameters because we know that there are 3 generations, and so I should really put generation indices on all of these fields, and then there should be generation indices on this. So the most general structure actually introduces 3 independent, not necessarily symmetric, just general symmetry, 3 by 3 complex matrices. So that's 3 times 3 times, 3 times 3 times 2, 3 times 3 times 3 times 2 parameters, a very large number of parameters. In this context, it seems totally remarkable that the most general couplings of the Higgs field could be so simple. But actually, I think you guys already know how this works. If I give the Higgs an expectation value, that will give mass terms which link the various generations of right-handed quarks and leptons to the various generations of left-handed quarks and leptons. And then those will be mass matrices, and those mass matrices will need to be diagonalized. And so let's now think about what happens when you do that diagonalization. So let's start with the leptons. So let's write YL, which is a matrix. This is a matrix, a complex matrix of general symmetry, but such a matrix can always be decomposed as a unitary matrix, a diagonal matrix, and a different unitary matrix on the other side. For those of you who are fastidious about mathematics, if you take YL dagger, that's a Hermitian matrix, so it can always be diagonalized. If you take YL dagger YL, that's a Hermitian matrix with the same eigenvalues. The diagonalization of this produces UL. The diagonalization of this one produces UR. And the general structure of YL is as I've written here. Okay, now, can we get rid of these unitary matrices? Well, actually, in the standard model, the strict standard model, you can. You write E right goes to UR E right. So that will, in this term, eat up the U right. The also L goes to UL L will eat up the U left in this term. So this term now is completely diagonal. It's just basically now the Yukawa couplings of the 3 generations, the L of each generation, the Higgs field, and the E, the right-handed lepton of each generation. However, you can't quite get away with doing this transformation without consequences, because when you do this transformation, you have to transform these fields everywhere, and especially you have to transform them in the kinetic term. However, the kinetic term is just, let's take the example of L. L dagger I sigma dot del L. So the sigma dot derivative term, it's just L dagger L, and any UL that appears in here will cancel. The other term in the covariant derivative is the gauge action, SU2. But UL commutes with SU2 because all 3 generations have the same SU2 quantum numbers. So if I plug this transformation of variables into this term, it's entirely unchanged. The covariant derivative commutes with the change of variables. Similarly for E right. And so actually these matrices U completely disappear from the formalism and are never seen again. This is actually an amazing statement that one shouldn't take lightly. When I wrote the most general SU2 cos U1 invariant Lagrangian for the standard model, I explicitly did not assume lepton number conservation. But what I found is that the final form, after I go to these new variables, not only has lepton number conservation, but it has lepton number conservation separately for each generation. That is, processes like mu to E gamma, or tau to gamma times mu, are totally forbidden, not as a consequence of some symmetry that I've assumed, but just simply as a consequence of the structure of the standard model. Now, I explicitly didn't add neutrino masses to this. If you add neutrino masses, the neutrino mass term will catch on the UL, and there'll be some extra term from that. But fortunately, the consequences for processes like these are proportional to things like neutrino masses squared over the W mass squared. So totally, totally negligible. If you ignore the neutrino masses, this statement is true rigorously. Lepton number conservation, and in fact the lepton number conservation of each individual generation, is an output of the standard model. It's not an input. Okay, well now what about the quarks? Well, for the quarks, yes? So if they were Dirac, then you follow what I do for the quarks, and the same thing will happen for the leptons. Well, not quite. Let me come back to that in a moment. If they're Majorana, then the U right is immediately eliminated. And the U left will appear, basically the U left becomes the PMNS matrix. Okay, or rather, it's a little more complicated than that, but the U left appears in the PMNS matrix. Okay, but the PMNS matrix is proportional to neutrino masses. So it's only important when you discuss neutrinos, not when you discuss anything else. Okay. Now what about the quarks? Well, for the quarks, there's an up mass term and a down mass term. And so I should do this separately for each. So I should write, for example, D right goes to U right for the D. That is to say, the matrix that diagonalizes this mass term times D right. And U right goes to U right for the U. And in both cases, the same argument applies. These are electroweak singlets, so the covariant derivative term only involves U1. All three up quarks, all three down quarks have the same U1 quantum numbers. So this matrix will commute with U1. It will totally disappear from the theory. With the caveat that when I make a transformation like this, which is a chiral transformation of quarks, the phase of the determinant of this matrix will not disappear, but rather it contributes to the theta parameter, as Nathaniel already explained to you. But again, I'll let him take care of theta. We're worrying about everything else. When you do this with D left and U left, it's slightly more complicated. For the terms that are not charge changing, that is to say, for the photon and Z couplings, U left D and U left U are in separate terms, and they separately disappear. For the terms that involve the W couplings, we're going to have structures like U dagger, W plus sigma plus W minus sigma minus. Oh, sorry. Let me just write it like this. U dagger W plus mu dot sigma d left. And when I make that change of variables, this guy will get an extra term. U dagger w plus dot sigma ul d dagger the other way around d left. So the u's will appear in the charge changing weak interactions, but nowhere else in the theory, except again their phases appear in the theta parameters. Now, fortunately, in standard model phenomenology, there's a term for this. It's the CKM matrix. And so when we finally transform everything away, these mass terms that come from the Higgs boson become diagonal. Then you can immediately read off these Higgs couplings. We diagonalize the mass terms. We don't diagonalize the weak interactions. So the weak interactions retain a mixing matrix, which is the CKM matrix. As you folks know, there are 4 parameters in here that can't be transformed away. And so the final set of parameters of the theory are the coupling constants, the Higgs parameters, the quark and lepton masses, all of which can be arbitrary, equivalently the quark and lepton diagonal Yukawa couplings, and the 4 parameters of the CKM matrix, plus however many theta parameters you choose to deal with. It's a funny thing that these 3 parameters are involved in the gauge sector, and all the other parameters in the theory are involved in the Higgs sector. So if you want to know why the standard model has the parameters it has, this is a very small part of the problem. And as many of you know, it's actually even addressed by grand unification. If you have a grand unified theory, these 3 parameters are reduced to 1 parameter. On the other hand, all the other parameters I've written on the blackboard are just arbitrary numbers, and none of those numbers can be predicted within the standard model, which I guess some people, including me, feel to be a real deficit of the standard model. But this is the point. The whole mystery is in the Higgs sector. And maybe if we could learn more about the Higgs sector, we could get clues to this mystery. Okay. We will come back tomorrow to this philosophy that the standard model Lagrangian is the most general renormalizable theory with SU2 cross U1 gauge symmetry. And that'll be an important tool for building up the structure that I'm going to talk about tomorrow. Now let's get back to business. Let's try to discuss the thing that I promised you, the various couplings of the Higgs boson. Okay, so when the Higgs boson was originally introduced, I think people had the idea that it would be a heavy particle. And in particular, the most tempting thing to say about the Higgs boson is that if it should couple, couple most strongly to those particles in the standard model that are the heaviest. And if you look at its decays, it should decay to the states that are the heavy states of the standard model. Namely, the dominant decay of the Higgs boson should be to W plus W minus, ZZ, and TT bar. And so the original searches for the Higgs boson, actually at the Tevatron, one couldn't look for a Higgs that was heavy enough to decay to TT bar, but one could look for Higgses that were heavy enough to decay to W plus W minus and ZZ, and intensive searches were made. At the LHC, all of these modes are accessible, but of course the Higgs boson wasn't found there. Instead, as I'll describe in a moment, the Higgs boson was found at a mass of 125 GeV, which is a number sufficiently small that all of these major decay modes are forbidden kinematically. And so, well, is this a good thing or a bad thing? Well, it's a bad thing because it significantly delayed the discovery of the Higgs boson. On the other hand, it's a good thing because it's very simple how the Higgs can decay to these three decay modes, but it's also kind of boring. Whereas in reality, with these three decay modes eliminated, we have to look at the decay modes of the Higgs which are suppressed with respect to the ordinary standard model expectation. And suppressed is interesting because there are various ways of suppressing Higgs decay rates, and in principle, nature can take advantage of all of them. So basically, there are then three classes of Higgs decays that we can think about. The first one is, if the Higgs can't decay to BB bar, maybe it can decay to the next lightest things in the standard model, the next lightest fermion pairs in the standard model, BB bar, tau plus tau minus, or CC bar, or maybe even mu plus mu minus. Well, the list goes on. The lighter the particle, the rarer its decay. And here the suppression is basically mf over v squared. But mf over v, even for the bottom quark, that's a small number. And so other things can contribute. The next class of decays we can think about are decays which explicitly involve perturbation theory. So in principle, the Higgs can have a loop diagram where you have top quarks or W's in the loop, and then something can come out the other end. And this is suppressed because it's at one loop in perturbation theory. So there's an extra factor of alpha s over 4 pi or something like that. But because this one's already suppressed, this can compete. And that would be, for example, Higgs to glue, Higgs to gamma gamma, or Higgs to gamma z. And then finally, we can go back to what are supposed to be the dominant decays up here. Now, if the Higgs can decay to let's try and get this straight. If the Higgs were heavy, its most dominant decay would be to WW and ZZ on shell. If it is too light to decay to WW and ZZ on shell, it can then decay to WW and ZZ off shell, which is a diagram which schematically we can write as an on-shell W and an off-shell W that decays, let's say, to lepton or neutrino. So here we have a factor of alpha weak over some 4 pi suppression, and there's probably also a suppression that comes from the fact that there's a propagator here. So there's a some kind of m Higgs over 2 squared divided by mw squared or mz squared. Now the interesting thing is that, and so here there's some alpha s squared over 4 pi. So the interesting thing is that these three suppressions are all basically the same order of magnitude. And so then we get a whole spectrum of Higgs decays. Actually, there are 9 or 10 different modes that have branching ratios above 0.01%, and all of them are produced at the LHC if you produce a million Higgses a year, as Tao said. And in principle, there's a tremendous opportunity to study the whole variety of couplings of the Higgs boson. So maybe this is a good thing rather than a bad thing that the Higgs was hard to discover in the first place. Okay. I'd like to just go through and talk a little more systematically about each of these separate decay modes. So let's start with the decays to fermions. That's definitely the easiest one. At tree level, the diagram is very simple. It's just a Higgs decaying, let's say, to BB bar. It's very easy to compute that diagram. I leave it as an exercise to the reader. The answer is the rate of the Higgs boson decay to BB bar is alpha weak over 8 m Higgs times mb squared divided by m Higgs squared, mw squared. So this is the Yukawa coupling. It's normalized by alpha weak. I've just converted from the Yukawa coupling to G with this factor. It's proportional to MH. There's nothing else that's particularly special about it. This is exactly the expected magnitude of the effect. Actually, this is true for any kind of fermion, so maybe I should just call this FF bar, and let's consider the various cases. Well, first of all, for tau and mu, there's hardly any more work to do. You just open up the particle data book, you plug in the numbers, and you find that these gammas are something like 260 keV, and I think 8 keV. I have it in my notes, but my brain is not working as 9 keV for 125 GeV Higgs. These are, I should say, really small numbers. But that's just a general indication that because the Higgs decay processes are highly suppressed, the width is going to be very small. And that's something we're going to have to worry about to think about precision Higgs physics. Now, for quarks, there are a couple more things that you have to think about. Because, in principle, for quarks, there are two effects which are very important. First of all, the Yukawa coupling for the B, let's say, is proportional to MB, but the Yukawa coupling is a renormalized parameter, and we should bring it to the correct renormalization scale. So the simplest thing to say is this is estimated by MB ms bar of the mass of the Higgs. Okay, now, what is MB ms bar? So first of all, maybe I should ask you, what is the bottom quark mass? Sorry? Now, so this is ms bar at MB. Right, very good, thank you. So this has to be renormalization group run up to MH to get the number. When you do that, this number turns out to be close to 3 GeV. So the bottom quark mass is a little smaller than you would think it would be when you plug it into this formula. Secondly, there are QCD corrections. Now, you think about one-loop QCD corrections as being like alpha s over pi, but actually in this case they're a little larger. It's 17 over 3 pi alpha s. Of course, the logarithmic corrections are sucked into this MB ms bar of MH, and then there's a color factor of 3. So when you put all those factors together, what you get is an enhancement of about 4 over the formula on the first line. And the final thing you come up with is about 2.4 MeV for the rate of Higgs to BB bar. And now you should be careful in the same way about all the other quarks that appear. Maybe it's worth pointing out that these pure QCD corrections are actually extremely well known. My friends in Karlsruhe, Cheturkin and Kuhn, have computed those to NNNNLO. It's a masterpiece of technology, that calculation. However, in general, the two-loop corrections to the Higgs to BB bar from alpha times alpha s times alpha weak and alpha weak squared haven't been completely computed. And actually, I've been talking to Stefan Weinzierl and his group about whether they have some technology to compute those. Eventually, if we do precision Higgs, one will have to complete that calculation. So it's interesting. The leading terms are known, but the full answer is not known. Stefan is interested because it requires elliptic polylogarithms. So you can ask him what those are. Okay. This business of the change in the masses is actually quite interesting. Maybe I should just write down the numbers. So the appropriate values of M Higgs are, for the B, as I said, 2800 MeV. For C, it's 700 MeV. For D, it's 3 MeV. And for U, it's 1.5 MeV. So these numbers they're really smaller than the ones you're used to. And you have to use those numbers to plug into the formula. So for example, the branching fraction to tau is about twice as large as the branching fraction to CC bar. And I hope you find this counterintuitive. You know, the charm and the tau have roughly the same mass, we're used to thinking, because their thresholds appear in the same place. The charm has a color factor of 3, and there's big radiative correction, so you think it would be much larger. But the charm mass is so small when you go up to the Higgs boson that compensates, and in fact overcompensates. So when you work out all the standard model decay modes, this turns out to be about 56% of the total rate. These other numbers are smaller. I think this is, the tau is something like 6%, and the C is something like 3% of the total rate of the Higgs boson. So it's interesting to take a big piece of paper and get all these things straight. I'll show some graphs of this a little later in this lecture. For the next thing I'd like to talk about are these off-shell decays of the W. Actually, frankly, I don't have a lot to say about that, because if I were to say something, it would get very technical very quickly. Really what you should do, so I drew a diagram here with one W on shell and one W off shell. And that's a good place to start, but actually it's wrong by about 15%. And the reason for that is that in principle, both W's can be off-shell, or both Z's. And if you allow the W to be slightly off-shell, this one can be slightly less off-shell. So the Higgs can kind of cheat to put both W's a little off-shell and try and get the maximum effect. So I think all I'm going to do is show you the two-jet mass distribution. So can you see it on this slide? I really made a mistake here. So this is a tree level calculation for Higgs to W star and Higgs to ZZ star. You can see that the one W or Z is quite close to the mass shell, but it cheats a little toward the left-hand side of the curve, so that you can get a little further with the other one toward being on the mass shell. And once again, the suppression is the extra factors of, essentially over here, the extra factor of alpha W that you have to pay to decay it to the final state, times the square of the off-shell propagator. So it is really cut down if that one propagator gets very far off-shell. The final numbers are that the branching ratio of Higgs to W star, including all the various final state modes, is predicted to be about 22%. The branching ratio of Higgs to ZZ, you shouldn't think it would be very different. I mean, there's a factor of 2 from isospin. So you'd think it would be about 11%, but actually the answer is about 3%, because that extra Z off shell business costs you. And I don't have a good way to explain that. It's really, you have to look at the phase space calculation. Now, it's certainly worth pointing out that a subset of Higgs to WW is Higgs to 4 leptons. Now, as we discussed I guess on Monday, the Z to leptonic branching ratio is the smallest Z branching ratio. It's 3.5% per lepton. And if you have 2 leptonic decays, then you have to pay that branching ratio squared. So by the time you get to here, you're at a branching ratio of something like 1 times 10 to the minus 4, which is extremely small. Nevertheless, you've got the LHC, you've got 1 million Z's a year, 1 million Higgses a year, so you can pay this factor and get a handful of events in this mode. And that turns out to be fantastically interesting if you would like to check the quantum numbers of the Higgs boson. Because let's think about this in terms of the W and Z polarization properties that I talked about in the previous lecture. So you make the Higgs. First of all, you get, let's say, ZZ or WW. Let's say ZZ in this case, because that's what we're talking about. So for a scalar interaction, the Z's are polarized. When they're polarized transversely, the planes are parallel. That's because the amplitude is proportional to epsilon dot epsilon. If we had a pseudoscalar Higgs, the amplitude would be proportional to epsilon 1 cross epsilon 2 dotted into the other vector in the problem, which would be the momentum of the various W's. And so then the polarizations would be at 90 degrees with respect to each other. That polarization then defines the decay plane of the leptons. And so by measuring the lepton directions and figuring out what the average decay plane is, you can discriminate this possibility from this possibility. Also, you remember that when the leptons are very asymmetric, when one lepton goes very forward and the other one goes backward, so in the boosted state, the leptons would be asymmetric in energy. That's a transverse polarization. Whereas when the leptons are roughly equal in energy, or if you like, centrally produced in the Z rest frame, that's a longitudinal polarization. So also you can measure from this the predominance of transverse, let's just say it the other way around, longitudinal over transverse. Now, which should be larger? Well, basically the transverse Z's have couplings that are proportional to the gauge coupling. But as I explained to you yesterday, the longitudinal Z's have couplings that are proportional to the Higgs self-coupling, which is somewhat larger. So the prediction of the standard model is that the thing that dominates is longitudinal polarization with a parallel planes. Whereas in this case, what you would get is transverse polarization with orthogonal planes. So then the interesting question is, how many events do you need to separate these? And the answer is that 20 events is actually sufficient. So here, just for your reference, is a figure with all the various decay angles that you measure. This comes from relatively early in the LHC run 1. But what these are the likelihood distributions for the observed sample of angles given various hypotheses for the Higgs quantum numbers. So always the orange distributions are the standard model, and the blue distributions represent various other candidate models. And what you see is the exclusion of many of these candidate models already with really just a handful of Z decays. So this one is the exclusion of the pseudoscalar Higgs, spin 1, spin 2. The one that really impresses me is this one down here, which, as you see, it's just about a sigma and a half, but this has gotten much better with improved data. So the OH is the hypothesis that the Higgs couples like in the standard model to HZZ. The OH plus is the alternative hypothesis that the Higgs decays to Z mu nu, that is to the field strengths. So this is basically dominated by longitudinal Z's. This is dominated by transverse Z's. And the data can tell the difference and actually favors the standard model hypothesis over the alternative. This still might be there to some small extent, and we'll talk tomorrow about how you ferret that out. Okay. There's one more set of Higgs decay modes that I wanted to talk to you about, and that's the ones that come from loop diagrams. Now, let me ask you, how many of you, let's first think about Higgs de glue-glue. So Higgs de glue-glue, it's a very straightforward one-loop calculation. You have Higgs, you have top. In principle, there can be any quark in here, but it turns out the top quark dominates for reasons that we'll discuss in just a moment. You have gluons in the final state. Probably you should include the cross diagram that's needed for gauge invariance. And it's a triangle diagram. So there's a limit to the mathematical complexity. How many of you have actually done this calculation? Ah, excellent. The rest of you should follow their example. It is a very fun calculation. And what you will find at the end of the day is that the answer for the scattering amplitude, of course, you have to do it in dimensional regularization, because just like for the self-energy diagrams, the gauge cancellations are extremely important. So you use dimensional regularization. And when you're done, you come to the following peculiar result, that it's G sub s squared and some numbers in the denominator. There's a gamma of 2 minus d over 2. And there is a 2 minus d over 2. You guys who had your hands up, you remember this? Keep your hands up if you remember this feature. Okay, if you weren't paying attention, shame on you. This is a great thing, isn't it? So this is a finite answer, which comes in a very peculiar way from dimensional regularization. And let me ask you the next question. This always happens in what circumstance? Yes?
The Higgs doesn't couple at tree level to gluons, so this loop must be finite, because there's nothing to renormalize. There's no coupling to renormalize.
Oh, yes, it must be finite.
Right.
But why does it have to be finite in this crazy way? Anyone? Sorry? Well, yeah, that's one way to say it. I think a more precise way to say it is that this structure, which is the ultraviolet divergence times 2 minus d over 2, is something you always find when there's an anomaly. It's really the signal that it's coming from an anomaly. And in this case, the anomaly is the anomaly with respect to scale invariance. The top quark, as you said, doesn't decouple. It leaves some remnant, which is the breaking of scale invariance. And so if the Higgs is very light and the gluons are very light, still through the influence of the top quark, the theory knows that scale invariance is broken through the top quark breaking of the scale anomaly. So let me give you now a derivation of this result, which makes this a lot more clear. And I hope you find it illuminating. Okay. So what I'd like to do is to think about this in the following way. Let's write an effective Lagrangian. Delta L is equal to the Higgs and gluons. And at the lowest dimension, there's only one thing you can write. It's the Higgs F mu nu, A. And let me just get straight in my notes. I put a 1/4 in front of this in my notes, so let me do that here too. Okay. And then the rate of Higgs decay should be proportional to A. And from this effective Lagrangian term, you can just work it out. So that's good. So in fact, the Feynman rule that this yields is minus IA times, if these gluons are called K1 and K2, it's K1.K2 G mu nu minus K1 nu K2 mu. And then you can square that up and get the rate of Higgs decay. And then that turns out to give you an answer, which I guess I don't have it here. I will write that eventually. Okay. So now the whole question is, how, when you integrate out the top quark, or some other kind of quark, do you generate this effective interaction? And so the first thing that's interesting is to estimate the size of A. So A is going to come from a diagram like this. A is obviously proportional to G sub S squared, and it's proportional to a bunch of other things. It is obviously proportional to the top quark Yukawa coupling, so let me write that here. And then A is also dimensionful, so it's got to get dimensions from the integral which appears when you calculate that loop. Now, A is multiplying a dimension 5 operator, so A has the dimensions 1 over mass squared. And so its dimensions are either from the Higgs mass, or whatever is flowing, whatever is the size of the momentum flowing through the loop, or maybe if there's a top quark particle in the loop, from the top mass. And in general, it'll be the larger of those two. Whichever is the larger of those two will dominate the dimensional analysis of this Feynman integral. Now, there are then two cases. Let me change this to YF so I can think of different quark flavors. If I have a bottom quark, this is G sub S squared MB squared over MB over M Higgs. And you see that's got a suppression in it. It's a small number. Yes?
Why is it 1 over mass squared?
Sorry. I should have written mass to the 1. So this is a dimension 5 operator. So its coefficient is 1 over mass. So there was a slip of the pen. Thank you for catching it. So that's either this or this. Depending on which is larger, that will dominate the suppression that comes from the loop integral. For the bottom quark, the estimate is this. And that's, as you see, suppressed by the same factor that suppresses the direct branching ratio to BV bar. On the other hand, for the top quark, it's G sub S squared MT over T times 1 over V. The Yukawa coupling is proportional to MT. The diagram is proportional to 1 over MT. And the result is that this is actually independent of the top quark mass. This is probably actually a very strong argument against the existence of a fourth generation. Of course, now LHC has explicitly searched for a fourth generation and ruled it out over the allowed range. But before that was done, one could point to this. If there were a fourth generation, it would also contribute in this diagram. It would also contribute in the same structure. And it would also contribute a term of that value. And so then the coupling of the Higgs to glue-glue would be 9 times what it is in the standard model. The thing that I especially like about this is the kind of ghostliness of these effects. The Higgs to glue-glue is dominated by the quarks which cannot be produced in Higgs decays, while the quarks that actually can be produced in Higgs decays are irrelevant. Actually, they're not really irrelevant. This term here comes to the first power. It interferes with the top quark contribution, and it gives a correction which is at the 10% level. So to be really accurate, you have to include the bottom quark as well, but it plays a minor role. Whereas any quarks that cannot be produced in Higgs decay play the dominant role and actually all an equal role. This is very analogous to what I told you about the S parameter in the last lecture, that the very heavy quarks, they're not visible, but they contribute a constant factor additive to the S parameter. Okay, so now we've discussed all the systematics of this diagram. Let's actually try and get the number. So there's a kind of fun way to get the number, which, as I've told you already, is related to the breaking of scale invariance by the top quark. What I'd like to do is to start with the top quark QCD vacuum polarization. So that would be the diagram without Higgses sticking out of it, which is just gluons and a top quark loop, mu nu. And you can compute that diagram, or you can just look it up in my book. And the answer is, if the momentum going through here is k, I k squared g mu nu minus k mu k nu times the trace of ta tb for color times alpha s over 3 pi. That's a number that you'll find in the, I guess, chapter 7 of my book. And then there's a log of lambda squared divided by m top squared. Okay. So that's the vacuum polarization diagram. It's some effective vertex that you would like to add to the effective Lagrangian describing low energy physics. Now what's interesting about this is that m top is proportional to v. And so if I want to know what the Higgs coupling is, I just differentiate this with respect to v, and there it is. So if I have, and now this becomes exact in the limit where the momentum of the Higgs goes to 0, I get I k squared g mu nu minus k mu k nu, 1/2 delta AB, alpha s over 3 pi, a minus sign, which actually is not particularly relevant. And then, as you see, there is a, when I differentiate with respect to v, there's a 2 over v that appears here. And so what you finally find is that this is k squared g mu nu minus k mu k nu times alpha s over 3 pi times 1 over v. And now we can compare that result to this result. So you see that we've now determined the parameter a. A is alpha s over 3 pi v. And now we can go ahead and compute the decay rate of the Higgs to 2 GLU. And what you get is gamma is equal to, I'll write this down, but it's on the slide, so don't worry about it too much. Alpha weak, alpha s squared, 72 pi squared, and m Higgs squared over mw squared. Okay. And as I said, with respect to ordinary expectations, there's an alpha s squared over some pi's suppression. So that brings this down into the order of magnitude of all the other processes that we've been discussing. And maybe I can just say that by an extension of this argument, you can go through and discuss how this works for gamma gamma, or for gamma z, of course, the z is massive, so the calculation's a little more complicated. Also, you'll find in the lecture notes the full expression. So this is the result in the limit when the Higgs mass becomes very small compared to all other masses in the problem. When m Higgs over m top cannot be... Oh, sorry, there's a question back there. Can I answer it?
Yeah, I just wondered what the H was, so you could explain how the A and then
I'm sorry?
The H in this effective.
H?
Yeah.
H is the Higgs boson field.
Yeah.
Okay. So the rest of it is the Higgs coupling. Okay. Okay, so there's a longer expression, and it's actually for those of you who like doing Feynman integrals, it's a fun exercise to get that expression. So that's an interesting challenge. I guess just to close the loop, this diagram is also the contribution of the top quark to the QCD beta function. And so that makes it explicit that it's the scale invariance violation due to the top quark, which provides the anomaly, which eventually lets this effect be non-zero. Okay? You can, in the same way, estimate in the m Higgs goes to 0 limit the rate for Higgs to gamma gamma. For Higgs to gamma gamma, you should include the top quark loop and also the W boson loop. And the W boson, so now you're interested in the contributions of these things to the SU2 beta function. And the SU2 beta function gets a contribution from this as well as this. And actually, these contributions are of opposite sign, because as you remember, the SU2 beta function is is positive from the top quark. From the W, there's asymptotic freedom, so it's negative. So there's a relative sign difference between these, and actually the W contribution is dominant. I think the expression that I have in my notes is minus 21/3 plus minus 4/3 the top charge squared. So this is from the W, this is from the T. There's some ugly prefactor that multiplies this that you'll find in the slides. Okay. These numbers are somewhat large, so the branching ratio for Higgs to glue, it's about 9%, the prediction of the standard model. And the branching ratio for Higgs to gamma gamma, you have to replace alpha S by alpha. So this gets smaller, it's 0.23%. So this is, again, 10 to the minus 3. The other mode that we talked about a little while ago, the Higgs to 4 leptons, is 10 to the minus 4. But the major modes are all of order 10%. The B is the exception. That, in the standard model, is predicted to be about half of all Higgs decays. And so finally, you can put the whole picture together. And lots of people have done that. This is from the LHC Higgs cross-section working group paper. And it's fun to stare at this curve. And maybe I should say, if you have the time, it's really worth making this curve for yourself in at least a rough approximation. So this is the standard model prediction for the Higgs branching ratios as a function of the Higgs mass as you go from 80 to 200 GeV in the Higgs mass. The observed value of the Higgs mass is the vertical line at 125. And so you can, just going from top to bottom, you can read off all the branching ratios. And please notice it's also a log scale. BB bar, WW, off shell, 23%, glue glue, tau tau, charm charm, ZZ, and then at the 10 to the minus 3 level, gamma gamma and Z gamma, and then way down there, mu plus mu minus. Actually, if someone could tell you how to measure Higgs to strange, it would be just about at this level as well. So that in all is 10 Higgs branching ratios above a branching ratio of 10 to the minus 4. There are interesting features to this curve. You see that when you pass the W threshold, W very much dominates. Everything else goes away. this little dip here is a funny feature. You may want to think about why that occurs. So I'll let you think about that. The real world is the red line where I've drawn it. Okay. And here are the numbers, which hopefully I've gotten most of them right. I told you that the B, which is about half the width of the Higgs boson, the width from the B itself is 2.4 MeV. When you add everything up, it turns out to be 4.1 MeV, and with the branching ratios that I've shown you here. When in the Higgs Discovery Seminar, where the ATLAS presentation was given by Fabiola Gianotti, she showed these predictions, and she said, "Thank you, nature," because the fact that these numbers are all so close to equality is totally unexpected. And it really is a wonderful tool, because as we pick off one after another of these branching ratios and measure the rates with precision, it allows us to probe the entire range of Higgs couplings to the various particles of the Standard Model. Okay. Well, now I started 15 minutes late, so I'll try and end early, but I want to take a little of your time to just go through the study of these couplings at the LHC and try and tell you a little about where we are now. So we're almost done we're essentially done the blackboard. The rest is a slideshow, but I hope you find it interesting. So at the LHC, you have to understand, of course, what the cross-sections are, the dominant processes by which the Higgs is produced at the LHC. Tao just told you all about them, right? So someone can just reel them off right now. The 4 dominant processes by which the Higgs is produced at the LHC. Would you review your notes, somebody? Who is eager? You're eager.
Gluon fusion.
Okay.
Vector boson fusion.
Yep.
Higgs-Strahlung. And TT bar Higgs.
Yes. Glue mainly to TT bar Higgs. And interestingly, all of these reactions have different virtues, which it's probably worth talking about. The dominant cross-section is glue to Higgs. It's basically just the reverse of the process we just described for Higgs decay. This is numerically the largest. As you see, it's an order of magnitude larger than any other Higgs production process. This is, by the way, the LHC energy from 7 to 14 TeV. 1 picobarn is here. So here we're at the level of tens of picobarns, which for an LHC exotic process, it's a large cross-section. Unfortunately, it's not always easy to trigger on Higgs decays, because, for example, the top part cross-section at the LHC is close to a nanobarn. And a lot of the Higgs decays get backgrounds from various kinds of top decays. In any event, the QQ bar going to a vector boson in a Higgs is nice, because the vector boson can be used as a trigger, and maybe I should say better, as a tag of the Higgs. Of course, there are also processes like QQ bar goes to 2 vector bosons, W plus W minus, or WZ, really, and ZZ are the backgrounds that you have to worry about. But nevertheless, the V can provide some selection from just run-of-the-mill QCD events. The vector boson fusion, where, as I described yesterday, the quarks emit W bosons, so this is UD W plus W minus to Higgs, gives you a process which is basically an electroweak process. And the things it competes with are other electroweak processes. For example, Z production in the same channel. And so this is a process which is rarer, but the background can be suppressed for various kinds of investigations. And of course, if you want to measure the Higgs coupling to the top quark, you'd better have top quarks in your event. And so then you have to go to this process. So here are the cross sections. As you see, the TT bar is the smallest, although that grows relative to the others with energy. Okay, now, how do you discover the Higgs? Well, as we will discuss, just because you're making Higgses doesn't mean you can see Higgses, because at the LHC there are many background processes that have to be accounted, many of which look exactly like Higgs events. So for example, as I've said here, you could have a process which is QQ bar to V and a Z. This has a larger cross-section than the Higgs cross-section. The Z mass is different from the Higgs mass, but it might be mismeasured. You can also have V plus a gluon, which is, let's say, splitting to BB bar, or to tau, or a photon or a Z that goes to tau plus tau minus. So all of these have to be taken into account as backgrounds. And at the LHC, as tau stressed to you, you don't have complete control over the kinematics. So there's some difficulty in distinguishing the background processes. So there's one thing which is totally unambiguous, which is to find a channel where you see all of the final states of the Higgs in a low background situation, and you can just make the plot and see a bump. But unfortunately, there are only two Higgs decay modes with that property. One of them is Higgs to gamma gamma. Oh, maybe I should just go over here. Higgs to gamma gamma. The other one is Higgs to 4 leptons. And, well, what can I say? There are no other ones. Higgs can go to BB bar, but GLU can go to BB bar. And actually, if you ask what is the rate for GLU to BB bar, where the BB bar pair has the mass of 125 GeV, it is 1,000,000 times the rate of Higgs production. And so it's very frustrating. Now here, these modes are very visible, but they have branching ratios which are 0.23%, and this one is 0.012%. So these are very rare processes. And so you can discover the Higgs in these processes, but only if you're prepared to look for processes that have rates which are respectively 4 times 10 to the minus 13 and 2 times 10 to the minus 14 of the proton-proton total cross-section. So amazingly, experimenters solve that problem. I think it's not time to discuss everything you need to solve that problem. Among other things, you have to throw away enormous amounts of data without looking at it and hope that you've thrown away the right stuff. But when you finally do that, you can come up with these plots that you've seen before. So here's the CMS plot of the gamma-gamma invariant mass with selections for the regions where GLU to Higgs going to 2 gamma is supposed to be dominant. There is a visible enhancement on this plot, and it's at 125 GeV. And at the same time, the Higgs to 4 lepton signal is much more apparent over background. But please look at the numbers here. This is 20 events per bin. So this is a really hard discovery, and I think the people who made this discovery deserve ample credit for doing something that most people would say is totally impossible. Okay. Now, maybe we should go to the other modes and think about how they could be seen. It gets harder. So, for example, if you think about Higgs to WW, this is produced in the reaction GLU to WW. W's are seen unambiguously as leptons. And so what you see is dileptons plus missing energy. And then, unfortunately, there's also a process, which is QQ bar, goes directly to WW, which produces dileptons plus missing energy. And the kinematics of these two processes are distinguishable, but let's just say they strongly overlap. The discovery plot for Higgs to WW is this one. Actually, what is this? This is, the leptons are muons and electrons, and then this is with 0 jets and with 1 jet. The Higgs contribution to the signal region is what you see in red. The W contribution to the signal region is what you see in the first purple band. The yellow is the what comes into the signal region from TT bar production. And actually, in this analysis, and I think in subsequent analyses, the events with 2 jets and up are unusable because they're completely dominated by top quark production. So, so here we are. You can see the data points, and you can see that the data points are totally inconsistent with removing the red region. Nevertheless, it is a struggle to compute all of the backgrounds, subtract them, and show that something is left over. In 2018, Atlas showed this curve, which actually shows that the analysis has been improved by quite a bit. Although, please notice that these shaded regions are the systematic errors in each bin. So it's still, maybe I should say, not completely obvious until you really do the statistics carefully that the red is actually necessary to explain the data. Okay. For tau, using the main production mode is considered to be impossible. And so there, what we want to do is to look at WW fusion to tau into some tau decay mode, like, for example, tau goes to mu and, Higgs to tau plus tau minus. And then you have a muonic tau, which is a tau plus neutrinos, and maybe a hadronic tau on the other side. That is a very low multiplicity, a multiplicity 1, for example, jet on the other side. This can be significant in the WW fusion region. Of course, there's also a WW goes to Z, which also decays to tau plus tau minus, fortunately, as I've said, with a small branching ratio. So one has to distinguish those, and you distinguish those on the basis of the reconstructed tau mass. Here again is a kind of discovery plot for the Higgs to tau. The thing which is obvious on these plots is the yellow histogram, which is the estimate of Z goes to tau tau. Now, actually, you can make that estimate very precisely because Z also goes here to mu plus mu minus. And then the same number of mu's and taus. So you measure this, you can estimate that. We know everything there is to know about tau decay. It's very straightforward. The other things here are a little harder. In principle, this process of just ordinary W plus W minus production, where this maybe is replaced by remnants of a hadronic W decay, can come into the analysis. And so that produces, if I remember correctly, the red stripe in the backgrounds. And the Higgs contribution, it's this little clear boxes here. Once again, in 2018, or rather 2017, oh, sorry, I'm on the wrong page. This is improved, but the status is still, I must say, not ideal. Again, the Higgs, W, QCD multijets. Here it just says others. There are many processes that contribute to this, all of which have to be estimated. These little boxes are the Higgs contribution to the signal region. Okay. Finally, the really hard one, as if these weren't hard enough, is the Higgs to BB. Because the Higgs to BB, as I've emphasized to you already, is easily buried by QCD reactions. And so what you want to look at is something like QQ bar going to a vector boson plus Higgs going to BB bar with backgrounds of vector boson Z and Z going to BB bar and vector boson glue, which is a very dominant process at the LHC, with the glue splitting to BB bar, which can always happen. And the BB bar is way above the B mass, so this is just basically a QCD splitting process. These modes can be distinguished here by the mass, if you can measure the B mass accurately. Measuring the mass of a hadronic system is harder than measuring the mass of a leptonic system. Here, the glue produces BB bar in a continuum. And so what you have to do is to estimate the background by sidebands and then extrapolate into the signal region. And it's thought that with machine learning, one can actually improve the estimate of this background using color flow. Although I'm not sure if that comes into the current analyses. Maybe if anybody knows, you can correct me. Ultimately, there's a different color flow in this reaction because the gluon is a color octet. And one can get some improvement by making use of that.
What is the final state?
Sorry? I'm sorry?
What is the final state?
The final state of
BB bar?
2 jets, which are B-tagged. Okay. So, this is a beautiful picture. This is a candidate for WW fusion to Higgs decaying to tau plus tau minus. This is obviously a muon. This is an electron. This is a hit in the electromagnetic calorimeter. There are 2 forward jets. It's a beautiful event. It's probably a WW fusion to Z, but there's some chance that it could be a WW fusion to Higgs. Okay, here is the current, I think as of a few weeks ago, Atlas analysis of Higgs to BB bar. There's something a little complicated here, so don't be confused by it. This is a very tight logarithmic scale. But actually, you can see that all 4 of these backgrounds are roughly of the same order of magnitude. The red is the Higgs contribution estimated from in this background calculation. The slice here is coming from TT bar. The slice here is coming from VZ, and the big slice, which of course, because it's a log scale, is actually making a small contribution, is coming from VW, where the W has a hadronic decay that, because of the imperfection of B tags, imitates the Higgs boson to some extent. The horizontal axis is a machine learning classifier, which the Atlas people have been working on for many years. And as you see, it does succeed in producing an excess of Higgs-like events over background and the highest bins. And when you subtract the background and put it on a linear scale, that's what you see. And there you see there's a quite significant signal. They measure the rate of this process to 20%, which is, frankly, an incredible achievement. So, and this is what it looks like background subtracted. It looks a lot better. The gray area here is the Z to BB bar. Okay. And so here, another thing which is new this year is the statement by CMS that they have a significant observation of the TT bar Higgs process. If you look at this curve, you have to be a little sanguine about it. The obvious thing to do is to look at Higgs in the BB bar, and this is the measurement of a parameter called mu that I should formally define. But basically, mu equals 1 is the standard model prediction, and mu equals 0 is no Higgs boson. Mu equals 0 is here, so you're not so far away from it. The dominant decay mode of the Higgs is BB bar, But in those events, you have 6 jets from the top quark system plus 2 jets from the B system is 8 jets. And there's ample opportunity for combinatoric ambiguity. So the modeling is very tricky. On the other hand, if the Higgs decays to gamma gamma, then it's in some sense obviously a Higgs boson, although those events are more rare. And so what you see is that for the gamma gamma, ZZ, and W decays of the Higgs, there are significant signals, but the numbers are all over the place because of low statistics. Here, there's a large signal with a very large modeling uncertainty. But CMS says when you add it all up, you get over 3 sigma, and so we have observed, we have evidence for this process. And so that brings us to the conclusion. Sorry?
Sorry, could you tell me what's physically mu equal 1.5?
Oh, yes, I should define mu. So mu is the rate that you observe. Mu is equal to the cross-section for Higgs production times the branching ratio for Higgs to go into the particular mode that you're interested in, observed, divided by the same quantity as predicted in the standard model. Okay. And so there's a lot that goes into this. You need to predict the cross-section, you need to predict the branching, you need to predict the branching ratio, and then the top line is the observed rate. And so as I said, mu equals 1 is the data agrees with the standard model prediction. Mu equals 0 is you don't need the Higgs boson. And mu can be negative because there's a background subtraction.
If it's 1.5, does it mean there are more Higgs than should be in the standard?
It means that this rate, for some reason, is 50% more than there should be in the standard model. But you see what the errors are. And that could happen because this is too large, because this is too large, because the width, total width of the Higgs is too small. There are many reasons why that could happen, and if you see a deviation, you have to sort it out. We'll talk about that problem tomorrow. Okay, so on the next slide, we have the observed values of mu from CMS for all of the dominant branching channels: gamma gamma, ZZ, WW, tau tau, and BB bar. Here's 1, here is 0. 0 is strongly excluded. You see that the mu parameters are all measured to about 20 to 30% accuracy, and they're all in good agreement with the standard model. So far so good for the standard model theory of the Higgs. It agrees with the LHC data at its current level of perfection. And whether things could be hidden here because the errors are not at the 1% level rather than the 20% level, that's an interesting question which we'll take up tomorrow. Okay? Thank you very much. Yes?
I would just like to understand a little bit better the meaning of negative mu. You said something about negative mu, I think.
Oh, yes. So let's go back to the previous slide. So 0 is no Higgs boson. You see here they erased some area which is allowed by the data where mu is negative. So how can mu be less than 0? Well, logically it can't be less than 0 because that would have negative Higgs bosons. But whenever you have a signal region for which your signal is a small part and you do a large background subtraction, then you could always end up with a negative number of signal events. Sorry?
What's the meaning of that? I mean,
It means that somehow you've observed fewer events than you predicted for the background. And that can always happen. Okay? No, it may just mean that statistically your number of events fluctuated low. That's apparently what happened in this case. Yes? I'm sorry? Between?
exclude negative signal region. There's a physical possibility.
Oh, I'm sorry. You're absolutely right. So, so if there's a negative interference, and this is not a large effect. The Higgs is so narrow that it doesn't have large interference with anything, basically. But in principle, that's also true. If there's an interference term between signal and background, and it's a negative interference, when you subtract the background, your prediction could be negative. But I think it's not relevant here because the Higgs is very narrow. So, so the Higgs width is here, the Z is over here. They're not interfering. Okay. Other questions? There'll be a discussion section this afternoon. So if you guys have now looked at my notes and there are derivations that you don't understand, bring them to the discussion section and we'll talk about it some more. And other than that, we get to hear about the hierarchy problem this afternoon, so this will be cool. Okay, see you later.